Welcome back, everyone. And today we're going to begin our journey into drawing curves. There's nothing in WebGL that allows us to draw curves like Bezier curves, kind of like how HTML Canvas has that functionality. So we kind of have to build it from scratch, just like with everything else with our fungi engine. So the first thing we're going to do is quickly go through some changes to kind of set up the framework so we can actually start doing curves, because there's two types of curves. There's cubic and quadratic, and we're only going to deal with quadratic. We're going to deal with cubic. Cubic takes 4 points to define a curve, where quadratic only requires 3. Since I want to use this for splines and path following and things like that, I'm going to stick with cubic Bezier curves. So let's start off me showing you a new template. I'm calling this one app FBO. It's built off the template from the last lesson called template app, because we introduced the fungi app functionality to kind of take all that boilerplate code out of the test pages, so we have less to look at. In this version, it's pretty much the app version plus using our FBO. Our custom image, so we can do picking. So it does the usual, creates our FBO, sets up our regular textures, sets up our post shader texture, so we need that for our 2-pass FBO thing. And I also changed the renderer. The renderer that's part of the core, because originally in the last couple lessons, to do picking, we had to have our custom renderer set up. So I went back and changed it to the point where we can use it with a single pass, like we've always been doing for most of the lessons, and setting it up for double pass. So this way we can draw everything in our custom buffer and then draw that as a texture afterwards. So I changed the renderer to the point where the only changes really I need is this part, where I set up the pre-render and the post-render. So before we render, this is what we do, and after we're done rendering, this is what we do. So pre-rendering, all I'm doing is setting up which buffer that we're going to be drawing at. So when that happens, it does all the rendering, and then when all the rendering is done, I switch it back to the main buffer, the display buffer. Then I prepare the next item to render, which is our post quad, and we just draw it. So it simplifies it quite a lot. So this is the template we're going to be using today to really do our stuff. Another thing I upgraded was our camera controller. The only thing I really did is in our switch handler function, now there's going to be an on deactivate and on activate. So when we're switching from one state to another, we're going to have the ability to do some cleanup on the previous state and some kind of startup on the new state. It's helpful because I kind of actually did a picking class. So this way we kind of move that out of the way, and so we don't have to deal with that code too much. So that was the only real change for our controller class. So it's in our controller switch. Like I said, it's just these 2 lines of code. New event handlers. That's about it. In our fungi core, there's a couple of changes, which I forgot to mention a little something over here. One thing that I also decided to change is our UBO transform uniform, or UBO. I added Vec3 post camera. Added to the transform because most of this is camera related information. So I need this for a new shader that we're going to be using, and it's just good to have. And most often, if you're going to do any kind of lighting, you need the camera position anyway in your shader, so might as well make it part of this UBO. So, and the camera object is what updates this UBO anyway, so it'll update it with its camera view, it updates with the projection, and it'll update with its position as well. So it's nice to have. So all the shaders and all the other templates have been updated to use this new UBO, because now this is kind of like standard for fungi. So if I go back here, so because of that, here's like the first thing I'm going to do. So when the camera orbit, when you call it update, it would now include this section. So it'll update the inverted local matrix, the matrix, and plus the camera position. That's the one of the big changes here. So that's in camera orbit update. So we're moving on to the next one. Another change is there's actually a bug fix in shader util. I found a bug here, and this was lowercase. This needs to be uppercase. So fungi.shader. I don't know why it does it that way. Yeah, I need to look at this because I think when I fix this, this is wrong. Is it fungi.shader? Create shader. Actually, no. It should be this. Oops, I made a bug again. That's what should it be. It should be just shader, because if I create a shader and if the shader did not work out really well, just delete it. So sorry, I just realized that's the bug. Okay. All right. So next up, originally this function had these 3 lines of code. So when I did an update on a UBO, I only did it to one item, one name, one data. I fixed it up. I changed it so this way we can, like a lot of our other functions, we pass in an argument. So it'll be name, data, name, data, name, data. So it'll just loop every 2 to do. So this way I can do more than one UBO update in one go without calling it twice. Because I don't want to set the buffer, do the change, and then undo the buffer. It'd be nice to just to do it once, do a bunch of changes, and then undo it. So UBO updates got changed. Like I said again, these 3 lines were commented out and replaced with this. It's pretty common stuff. We've been doing a lot for fungi. Our next one, boom. Let's see, is this the same class? No, in our VAO. In our VAO, I added a new function called update array buff subdata. All it is a quick shortcut to update data that exists in a buffer, because we're going to do dynamic meshes, and we're going to modify pieces of the buffer. It's in today's lesson. So I built this function to kind of help us out. So all we have to do is pass in the buffer ID, the offset, and then data we want to update. So you'll see it in action today. What else? I think that's it. Now the only left big change is our renderer. Our renderer class, if you remember, the main function was really big. There's a lot of if statements because it had a lot of management done. What I did is I pulled it out. Well, first of all, we have here's the rendering events that, like I said, that the template now uses. That's, I guess, just start at the beginning of the function. So we have here's the new events for the renderer. This helps us manage the FBO custom rendering. So, if we don't want to use them, we don't use them, and then this will be what the function actually does. If we want to do custom stuff with our renderer, this gives us the ability to do it before and after, which gives us that FBO thing. So this way we can have one render class in the core, and we don't need to run any custom ones. We can kind of just add functionality to our new renderer. And a lot of the changes has been pushed into a new function called prepare next. And when done preparing the item for rendering, it draws it. And I just call it prepare next because it's this stuff. It checks to see if the materials are the same. All it does is try to limit switching back and forth between shaders. So, I explained this in previous lessons when we first introduced this. It's just optimization tricks to kind of limit as many GL calls to the GPU to switch things on and off. So if I have 5 items that have calling turned off, then I'm just gonna turn it off once. Then when those 5 items are done, and then the 6th item needs it, it turns it on. So instead of me turning it off 5 times and then turning it on 6 times, I'm only doing 2 calls instead of 6 calls to the GPU, just to change that one setting. And it's true with a lot of everything else. So this prepare next is just going to be added on to over time to add optimization to our render class. So this is in and that's really it. So that's our updated rendering class. All right, so now we're going to go to our spline.js file that we're going to create, and it's got a bunch of stuff in there. First, we'll start with picking. This new object handles our picking. It's I built it as a controller handler. So all we have to do right here, like remember we used to have a custom handler class object. Now this is the class object right here. So we just add pick, and picking is our object. So our camera controller will use picking, and then its down override will be used its picking down override. And if you don't remember what the override does, it does when you do the mouse down, it just checks to see is there a need to switch it to a new handler. So this, normally this should be its own function if I have a lot of handlers, but since I only have 2 handlers, which is the camera and the picking, I just threw it in here just to as a place to put it. So that's what our override does. So that override just switches us out to the new picking. Switches it to picking. So this way we can move the objects on the screen instead of moving the camera. We're going to start off at ID 0. So this also manages all the ID numbers. So we're going to start at 100. List. I didn't comment these, which just suck. List is the way this works now is that any object that I need to make draggable or clickable on GPU on the canvas, I register it. So the list just keeps track of all the objects that have registered on the screen. So right here's the function. So you register, you pass in the object that you want to kind of track, and the callback. So this sets up a callback. So I just implement the ID number. I create a quick struct or object. Save the ID number, save a reference to the object, and save a reference to the callback, and then I return back the ID. So the calling object or whatever gets the ID number that was just generated. So you registered. Here's the ID number that you get for registering with the picking object. And this kind of is a static global object, so you don't instance it. So it's a global thing. So anywhere in the code we can kind of just call picking, saying, okay, register this object for us because we need it. Find allows us to just search our list looking for the item that was picked. So when we pick the color from our color buffer, we're going to turn that color back into an ID number, and hence these next 2 functions. We had those originally in our test pages. Now they exist in our picking object, and we already explained that one. And we're using our new events for our controller handlers. So when this handler activates, it finds, it passes in the data, which is, I think, the ID number. So it passes the ID number, and I find it, and I save it as target, which is up here. So this whole object right here that's in list gets stored, or a copy of the reference gets stored in target. So this way, when we're, once the mouse down, like basically this one turned on this handler. So when this handler turned on, it's like, all right, here's the data. It saved the target, so it knows which object that was that the mouse down was happened. So target is the mouse down object. Mouse up, we switch the camera, the controller back to the camera. on mouse down. After the on down override, it switches to this handler. Now its own on mouse down event happens, which the only thing we're going to do is save the X and Y Z or X and Y position, the initial, because we're going to use the same thing we did in the previous lesson. We're going to use the initial position, and then we're just going to update it every frame while dragging, starting at that position by how much you've moved since then. And we save the initial position of the... Actually, I don't know. Do I even need this? No. Yes, I do need it because I need that for the delta. So that's I usually use that to calculate deltas, and I save the initial position of the target object. So the target has the object reference, and it's kind of a renderable, so it has a position. And mouse move is the dragging aspect. So this one just helps us calculate all the dragging. Grabs the delta of the current X and Y to the initial X and Y. Then from there, I make a copy of it, the original position. Then I add the left, and I add the up directions that you're currently moving. And then I copy that right back to the object, which is a renderable, and then I call the target's callback, passing in that object. You'll see the object that holds the callback and the actual target object. This part's a hack. It's a global var, not a nice way, but the next object coming up is something called dynamic mesh, and it's something I put together to help me debug and visualize data. I'll talk about it in a minute. So while we're dragging our points around the screen, we're going to be updating the position of our Bezier curve, and in our dynamic mesh. So we cleared the mesh, we update all the data inside, all the vertices in that thing, in that mesh, and then we do an update, which all it does was push all that data into the GPU. And then we also, not only we're using our new dynamic mesh object for debugging, we're going to use our debug lines as well to draw the lines between our position points and our control points. You'll see that in a little bit. So yeah, and it's a lot. It's to quickly go through. So here's dynamic mesh, and dynamic mesh is a very simple object. It extends the renderable. So the only thing it does, it creates an empty VAL. It creates a buffer on the GPU with a set amount of space. So you pass in your total vertices that you want. So, if I'm planning to create something and I want to debug maybe 20 vertices worth, maybe that's what I'll do. I just say, give me a dynamic mesh that can hold 20 vertices, and it creates that buffer space on the GPU, and that's really all to it. And it calculates it right up here, how to make the buffer size. How big is a float, how many bytes is a float, times 3 floats per vertice, and each, and how many vertices you want. So that's the buffer size. I like dynamic mesh because I want to be able to change the draw mode. So if I decide to take a dynamic mesh and I just want to do points, I just create dynamic mesh and then change its draw mode to points. And in this instance, I'm using a line strip by default. But I can also do lines, I can do triangles, whatever. Like I said, this is once I want this to be kind of a dynamic mesh object, so I can just reuse this for whatever I need to for debugging, or in general for anything really. If I just want to do any procedurally generated objects, this object will be really good. So I just wanted something bare bones that's useful for that's dynamic and useful for a lot of ways. And here it is the draw function, which is different from the renderable. It only draws if the VEO count is greater than 0. That means there's actual vertices pushed to the GPU. And it just draws with draw arrays. Down the line, I'll probably add an index, and then it'll just go back and forth to see if if it needs to draw with the index or draw with the array. Clear, it just kind of resets everything, wipes out the array, just change the VEO count because I don't want to render anymore, and I set it to false. Because if there's no data, I want it to be false. So when the renderer tries to render this, it checks to see if it's visible or not, and that's that. And the update function, all it does is kind of automatically handles the visible state. Then it updates the count based on how many vertices are in there. If there's, like I said, 3 vertices divided by 3 gives us our vertice count. And then this just pushes all our data back to the GPU. It kind of just fills up our buffer with the exact information based on how many vertices you pushed in there. So if you kind of create a dynamic mesh that you set up to handle 20 vertices, you don't have to fill it up with 20 vertices. You can fill it up with 1, 2, 3. The number you set is the maximum. So if you go over 21, you'll probably get an error saying you can't fill in. There's too much data for the buffer. So that's our dynamic mesh, which is going to be probably very useful down the line, and I'm probably going to move it somewhere under the fungi namespace. But for now, it just lives globally as dynamic mesh until I'm pretty sure I really like how this this class is put together. Then we got another static class called Bezier, and it only has 2 functions. First, we'll start with this. This one is the main thing that makes it all possible. This is the function, the Bezier cubic equation. And you apply the equations right here, and you apply it the same equation, but the only difference is which component of your vertex you're doing it. So it's really a rinse and repeat, just going from X, Y, Z, and then saving the X, Y, Z. So like I said, a Bezier curve is a curve that's drawn based on 4 points, and you have a time, and the time is a number between 0 and 1. It's kind of a lot of other things that we've been doing, like in GL. Like I said, everything in OpenGL centers around between -1 and 1 or 0 and 1. So timing is, like I said, a number between 0 and 1. It's basically a percentage. And so if you have like all these 4 points that define a curve, when you say time, it's like, I want 50% of that. And when you say 50% of that curve, it'll tell you the exact position in XYZ of that curve. So the way you draw a Bezier curve is that you take a curve and then you sample it. So if I want to draw the curve, let's say by default we're going to use a sample of 10. So that's what this function comes into play. So generate has an out, which is like an array. I forget what I originally called this. This is kind of like the sample, but I don't remember why I call it Reese. That's what I get for using bad variable names. It's not very descriptive, but I know exactly what it does. It is the sample rate. So, and then we pass in the 4 points. So when I pass in the sample rate, I want 1 out of 10, because so it's the increment. Like, so if I'm going to go from 0 to 10, what is the position? What is kind of like the position? It's kind of like we did Perlin noise. We just divide the amount of samples, and then we loop through that sample count. And we, here's our time, because we'll just I don't need time anymore. That was originally there because I was doing a bunch of things, and I think I eventually took it out. I did take it out, so I don't need time anymore. So yeah, so what we're gonna do is when we want to build the curve, we're gonna sample it by 10. Let's use that as an example. So we're gonna loop from 0 to 10, and we're gonna pass in our points, and we're gonna increment. So at the 0 position, what's the increment? So 0 times increment is 0. So at 0, give me the position. And then I push that position into our outer array. If it's 1, it's 1 times increment, and so forth until here I reach 10, which would actually be our number 1. Because at that point, we get that final point that's at the 1 position, at the maximum position, at the end of the curve, the actual dead end of the curve. And that's what this function does. So this is really the two main things we need to generate a curve. The function that calculates any point on the curve, and then a function that samples the curve by whatever increment you want. So let's say if we do a sample of 5, it's going to look very, jaggedy. You'll see it. I'll play around with it so you can see it. But if you want the curve to be really, really smooth, if you really want it really smooth, you do a sampling of like 20 or something, and you'll see how it looks in a little bit. I'll play with those numbers so you guys can see the difference. There's other equations. There's other things we can do. I'm just not implementing. I forget what they're called in Bezier Curves. I found some good tutorials and articles about it. It's a way to kind of determine how many samples works best for a specific curve. Because if you make the curve stretch out or make it curve in a certain way, you'll see the straight lines. It's not very smooth. So that means to make that smoother, you need to kind of sample it with maybe a couple more samples, or by putting, like, let's say if you have 10 samples, maybe 5 of them should be close to each other in the beginning and the rest at the end, based on the curve. So there's ways to calculate, ways to resample the curve more intelligently than just saying, okay, divide up the curve by 10, an increment of 10 or 20. But like I said, there's more to it, in which I'll probably maybe a point in the future, or I might in the description I'll put in the links to so this way you guys can go forth and do that before I implement something like that. It's a little bit more complicated. There's more math behind it. So, but like for now, I just want to start creating some curves without worrying about doing the best possible sampling in generating those curves. So now we're down to the last piece of this file. It's the drag points. We're going to actually have points, or the 4 points that create the curves. We're going to actually make them draggable. And our first function inside is get renderable, and all it does is set up some shader code and a material. That's all it does. It just creates this one stuff for this drag points. And then we have our constructor, which sets up a lot of our stuff, and we create another empty buffer, and this one's going to be different. This buffer is going to be a single buffer, but partitioned in 3 parts. We're going to have. Let me just go up to here. So we're going to save our points. So we're going to have 4 points. For our curve, and down the line we're going to do more than 4 points, but for now we're going to do 4 points, and we're going to just check if it's modified. And our vertex component size is 9, because let's say so each vertex component is going to be 9 floats long. The first 3 floats is going to be our position. The second 3 floats is going to be our color ID. And the last 3 floats are going to be the actual color that we want to draw. So instead of creating 3 buffers, or 3 attributes, I guess. Instead of creating 3 buffers for 3 attributes for a shader, I'm actually going to create a single buffer that partition is itself into 3 attributes. So up here, we have these 3 layout attributes, which is position, ID, and color. And that's what we're doing. Exactly what we're building. It's these three things for our shader. So, you know, so we create like I said, I create the empty buffer. I know what the buffer size is going to be. It's going to be the component size times what a float is worth. And we're going to give it our attribute position location. And it knows what it is by default. Kind of, not really. So that's 0. And how big is the component? It's 3. And our stride is how big overall is the entire component. Or the entire, each massive component. Like, I don't know why it's called stride. I don't understand the meaning of it. But that's what stride is all about. It's the total size that your each chunk of information in the buffer is. So, and we're going to say the first 3 belongs to location. Over here, we set to 1, which would be location 1 is our AID. So we give it our stride, and then we give it an offset. So we're going to say we want it to start at the 3rd vertex. And then on location 2, we set up our color, which is again up here. So we're setting up that one, the A color. Again, it's only 3 floats big, part of a component of 9, and the offset is 6. Because the first 3 is location, 0 to 2 is location, 3 to 5 is our ID, and then 6 to 9 or whatever is, or 7 to 9 is our color. Then we finalize it and we set the count. So that's, so this object, you know, sets up this empty buffer. And again, I'm using a default size of 20. Since I'm only going to use 4 points from now, I'm kind of overdoing it. You only really need 4, but I'm overfilling it because just in case down the line I want to add more points, which we're going to do in the future lessons. Let me get some water. All right, we got a standard draw function. We just alternates back and forth to see if it's indexed or not, which I don't think this one is. No, it's not indexed. So ideally, I don't need this. I can just say draw arrays and call it a day. But I just copy and paste this from another function. This one just adds points to our list. Oh, where is it? It'd be a constructor. So this time I'm calling it underscore points. I really don't like underscores, but it's kind of a JavaScript convention that if you want to keep something private, you give it an underscore name. So like these I want to be kind of a public and these I want to be private, but just because it's underscored it doesn't mean it's really private. You can still access it. It just tells the developer this is a private function, private property. You shouldn't really be modifying these directly. And sometimes you'll catch me modifying them directly because it's a way just to quickly hack into it. But yeah, I don't know. So yeah, so add points, create another struct, and I'm going to store the ID number, the color, the position, and its index. This will be index 0 if it's the first one. Then I register this point for dragging. So I pass in the object that I just created, saying, okay, you know, I want to register this. And I want the callback to be the update callback and bound to this instance of the object. I was just thinking that might be the easiest solution or the best way for now to handle picking. You just an object and a callback. So this way I can have different objects register draggable things on the screen and then have them, you know, have their own object and callbacks called when they need to. So that's really the rationale behind me doing this register thing. It's kind of like setting up an event if you're used to like C# and stuff. You know, you kind of just add event listener, or same thing with JavaScript, and remove event listener. So at some point, maybe I might have like an unregister function. So this way unregisters the object off the list. So this way it's no longer searchable, and I can just recycle that ID number. But that's for future things. So yeah, register, I get the ID, and when I get the ID, I actually update the ID. So I save it. So this object, I also save the ID number. So even though it's 0 by default, eventually once it's registered, I will save its actual ID number in there. And then I store it into our points array. And here's our callback. And so all we're going to do is going to pass in our object, and we're going to use the object's information to do our update array buff subdata. Now remember, this is the function I said earlier. So the idea behind this update thing is that, remember, like I said, this one does subdata, and we're going to pass in the buffer ID and the index times stride to kind of tell you where in the array I want to modify. So, and then position is the actual array data that we're going to push in, because remember the object has, remember this O that comes in is this object that we're passing in. The idea is that if I'm dragging a point, let's say I have 4 points in our array. So, let's ignore the fact that it's 9 components each. Let's say just 3 components. I'm just saving the position in an array. If I am moving just 1 point, let's say the second point on the list, and every time I drag it, I want to update it on the GPU, I don't want to have to resave the entire array. All, 4 times 3 is 12. I don't want to save all all 12 floats back into the GPU. So what, like I said, this function does is allow me to just update a certain portion of it. So this, I'm telling you the starting position. So let's say if I'm doing, let's say the second point, which is index 1, times stride, which is how long the components is. So for the example I was saying, it's like we're only doing 3 components for our buffer. So it'll be 1 times 3. So the starting position would be 3. And then it would then write anything that we pass in. So if we pass in like an array of 3 elements, 3 floats, it just writes into, starting there, it'll write 3 floats. If I were to some reason put 4 floats in there, it will write those 4 floats, but they will end up corrupting the data in a way, because now you're going over the bounds. You can do that. It's perfectly allowed to, but if you're not doing this correctly and you override more data than you should, you can mess up the buffer. It's kind of like manually, it's kind of like you're literally going into an array and saying, I want to modify index 1, 2, and 3. And that's it. I want to ignore 0 and I want to ignore 4. I just want 2 and 3. Those are the only parts of the array I want to modify. And that's what we're doing. We're just surgically doing that. So like I said, so if we have like 100 points on the screen and we make them all draggable, I don't want to have to update all 100 points worth of information. I just want that vector, those 3 bits of information, those 3 floats is all I really want to update. So if it's very efficient. It saves you time talking to the GPU. Like, you're not updating a bunch of data that you don't need to. So that's why that function exists that we created, and that's why we're using it. It's really here just to be very efficient, to surgically update our buffer on the server, on the GPU. Bind buffer, build buffer. So when we have all our points in here added, we have this thing to build our buffer. And it's kind of like with the dynamic mesh. The only thing this thing does, it actually creates the color, the CID, using all the function needed. So this is our 9 components that I was talking about that this thing creates. Here's the position, here's the color ID, and here's just the color to actually draw the point as, and just pump them into this array. We get its length, and then we push all that data we just generated into our buffer on the GPU, which then we'll use the update callback to just surgically update all this data. So this way I only need to modify that one little bit of the information every time I'm dragging. Like the rest gets to stay unmodified. And we're only doing for one versus I'm updating the entire array of information back into the GPU. And that is the end of our spline.js file. Feels like it took forever to explain that. So now we're going to our test. Like this is pretty much the template that I mentioned in the beginning. So it has all the same stuff. Now the only big difference is here we're going to prepare our renderables. So I'm creating our 4 dragging points. I build a buffer. I add it to our scene. I create our dynamic mesh. Bezier Curves. So I'm just initializing our Bezier curve. That's what I'm doing here. Update it again, and then put in our scene, and there's a quad. And everything else is practically the same. The only thing I did is probably I commented out this information and just changed the color, hard coded it to black, and set the point size to 8. And that's about it. So that is the HTML portion of it. So now if we go back here, this is what it looks like. Now there should be lines between the position points and the control points, but I don't initialize it. So if I click it just once and do a small little drag, the lines draw in. So this is me being lazy. I just didn't want to add more to it, because once I start dragging, it automatically updates. So here is our Bezier curve. The black line is the curve that we're creating 10 elements. It's sampled, and you can probably see where each point ends, or where each point exists. Let's see if I can modify it so this way it's more noticeable. So if I go up here, and when we're dragging, the unmouse move is when we're dragging, it regenerates the curve. So I'm making a sample of 10. So let's make a sample of 5. If I go back here, refresh, it looks the same, but once I start dragging, there you go. You'll see that there's only 5 points. There's 1, 2, 3, 4, 5, and 1 more. So whatever you say, whatever number you say is +1 really, because you need that last point. So there you go. There's our dragging points. It's hard to get the points because sometimes I touch the lines and that's overlapping. So yeah, you can move the control. Whoa, get that green just right. So here you go. I was doing so much better before. So this is what it looks like with just 5 samples. So let's see what it looks like with 20 samples. The curve should be much more smoother. So we refresh. The curve looks much better. Like you don't notice too much. You'll notice if I make it short, then you won't really notice much. That's why those other equations or like algorithms to determine the best sampling based on the length would be useful. Like if I want to do something like really far out, then now you'll start seeing where the points begin again. It's no longer super smooth, because it's based on length. So the longer it is, the more curvy it is. Like doing it this way, that curve breaks. Like over here, like this should probably have more samples, like concentrated in this area. But yeah. So yeah, this is kind of great. And based on our position, that's where we move it. So I just move things around. So that's what our curves look like in 3D. So you move right here. So that's what our curves look like in 3 dimensions. So this is pretty sweet. I love this. This is fun as hell. I created this like months ago in 2D because I was doing I was studying splines, and splines are Bezier curves but that continue. You can keep adding on and on and on as many as you want. And Bezier curves or splines, that's where I kind of learned from Unity 3D, is that that you can use them for a lot of stuff. What got me really interested in was procedurally generated meshes based on splines. Just like how we are sampling the points and then drawing a line between each point, that's what we're really doing. Like, that's, once we have each sampled spot, we just draw a line that connects the dots. Oops, it's hard to get that point. Let me just refresh. I started beginning. So I forgot what I was talking about. Oh yeah, what got really into it is that while we're sampling, we're drawing a line. What we can do is that we have that point. We have to determine. I think it's tangent, it's normal, and I think something called binormal. And if once we determine all that information from that one point, we can actually take a 2D mesh, let's say a square or a triangle, whatever, and we can put it there at the right angle of rotation, whatever, in that one spot. And at every sample, we can add that piece of mesh. And then based on how it's built, we can probably use triangle strips or just regular triangles, and then just connect the dots as triangles. And then this way we have a mesh. So think about like a road or like a racetrack or whatever. And as I move this line, that road actually dynamically morphs into that follows this path and follows that rotation. So that's the idea. That's where we're shooting for. That's the goal for the next couple videos, is to take a single Bezier curve, make it continuous. So this way, you have 4 points, and then at this point start another Bezier curve. Then when that one's done, start another Bezier curve, and on as many curves as we need that get combined, and maybe build different type of control points. Some that are mirrored, some that are independent. So this way you can make some really funky curves. So once we start adding curves together, then you call them kind of like splines. And then once you have a spline, a nice continuous spline that you can kind of just customize, then we can do some fun things with it. Like I said, we can extrude a mesh across it, so this we can build dynamic or procedurally generated meshes that way. You can create waypoints for movement. So maybe in the next lesson or two, once we have the spline together, I'll have like a cube that will move on this line back and forth. So it'll just drive back and forth. It'll use it as a path of movement. So like if you have an NPC, you can basically this will most likely be more of like an editor tool. So you kind of create, use all these control points and UI components to build a curve. We save the curve, and then we can use that curve for meshes and movement and whatever else you can really do with these. So there we go. This is Bezier curves. I'm going to post the links. Coding Math had a great tutorial on the mathematics and the concepts of Bezier curves. So you can kind of see how Bezier curves are drawn, or the equation basically is lerping. It's really cool how it illustrates how it works and mathematically how it actually works. Excuse me. So yeah, I'm probably rambling on now. Probably late. Yeah, it's 1 a.m. So yeah, there's Bezier curves. So next lesson, we're gonna make these into splines. And then maybe after that, we'll do some animations, some movement, follow the line, and then hopefully do some extruding, and God knows whatever else we can come up with. So let me let me get out of here before I cough myself. Allergies are also managed to last this long without coughing too much. All right, so like, subscribe, comment if you have questions or suggestions. See you guys at the next lesson.